Thank you, everyone. I'm happy to introduce our next speaker, Dr. Mohamed Shaaban from Scale AI. He's the Global Director of AI Product at Scale AI. He's a physicist and a technology leader with a distinguished career at the intersection of aerospace, AI, and national digital transformation. He has served as a mission lead for the SuperBIT Space Telescope, a joint NASA, CSA, Princeton, Toronto program. He has pioneered next-generation observational astronomy, and please join me in welcoming Dr. Mohamed Shaaban. Thank you.
Testing. Great. Thank you for the great introduction, and thank you everyone for having me. I'm excited to be here. As you just heard, I'm from Scale AI, and I'm excited to announce that I'm about to give you the least technical talk of the event, but hopefully extremely informative from a very different angle. The talk I want to give, I call it Lessons from the Field. This is sort of the mirror of a more technical talk. And to explain what the field is, I have to first kind of give you a little bit of an introduction of what Scale AI does. On a large scale, our goal is to build reliable, high-impact AI systems. And I know what you're thinking. You're like, I've heard this sentence before. Everyone says this sentence. What does that mean specifically? For us, it means two things. There's sort of two components to our business. The first component, which you see here, is the research and data arm, the one I will not talk about too much today, because everyone here are expert technical graduate students and postdocs who are very familiar with that kind of work. That arm of the business's goal is to help model builders, so traditionally large model builders like those who build LLMs or those who build self-driving car models, improve their systems on both reliability and accuracy. So there is a measure component where we work on Evals, we work on guardrails, loss bucket detection, red teaming. And then there is a react to the measurement component where we do data creation, data labeling, data annotation, RL environments in order to enable these models to improve against these measured metrics. And this arm of the company enables us to think very deeply about the future of the technology, but it also enables us to have an interesting insight of where things are going. And then we take those insights and we use them in the second arm of the company, where we specialize in essentially delivering outcomes. We work with enterprises and governments to understand pain points that they have, and then we build custom AI-in-the-loop solutions to address those pain points. Now, where does this whole lessons from the field thing come in from? We're one of the only companies, actually one of two, that does both of those things. And even within our company, we've noticed that the so-called touch grass problem, the correlation between the more academic, research-oriented, model-oriented lens of the world and the much more applied in the field, systemic impact on society world are highly uncorrelated sometimes. So the goal today is to talk about what are things that we've learned on the application side by being in the field, seeing things in production that might be interesting to know as someone who is an expert on the technical side of the world, especially if you're interested in joining industry after your academic career. Which, you know, sort of one of my secret missions on this trip is recruitment, hence the nature of the talk. All right, so you'll hear me say the field. When I talk about the field, I mean applications business, working with governments and enterprise, and then you'll hear me say the academic lens. There I'm talking about our still enterprise work, but with research labs that are trying to make models measurably better. So the first thing we've learned in the field that I'm assuming everyone here has already learned from being on the internet is that the absolute majority of attempts to productionize Gen AI have been unproductive. You'll see various stats about the extent to which these use cases are failing. Specifically, when they say failing, they actually mean one of two very concrete things. Failure mode number one is you build a solution, and this solution just never goes into production. Stays in pilot hell forever or gets decommissioned before it ever gets active users. And the second mode of failure, which is sort of the worst one in my opinion, is it goes into production and provides no real quantifiable value, whether it be economical value or work experience value or soft value for the daily active user. So the first thing we've learned over the past 6 years or so is that this is definitely the case. The failure rate's really, really high. And we've been trying to understand, and I've now kind of fully understood, why is that the case? And the answer is there's sort of two reasons, or two reason categories. There is people building the wrong what, which is you're just building the wrong solution or the right packaging for the models, or the wrong how, which is a little bit more exciting, and I'll explain why in a second. But this is about the delivery mechanic. People are incorrectly using a mechanism of delivery that does not work with stochastic systems. And you'll see the ratio here is because as of 2026, most folks that are operating in the field have sort of figured out what the right what is. It tends to be sort of more smaller organizations that are still working with the wrong what. And the wrong how ends up being the dominant component for why these things fail in the field. Okay, so I'm going to talk briefly about the right what first, break it up into components, and then we can talk about this how. At a high level, the right what has two signals. There's two smell tests. If I build something in production for an enterprise or a government, it needs to be, one, useful today. One of the failure modes we see are people are often trying to forecast the performance axes of various models and build systems that are non-functional right now, but will quote unquote be useful in the future. So lesson number one on the right what is you build a system that is useful today. Lesson number two is you want to target systems whose usefulness is either independent of or couples to the scaling laws of the technology. So you want to build a system that will not get deprecated as the technology improves, and ideally you want the system's performance to improve as the technology improves. You're like, great, what does that mean? These are very high level, let's get specific. So specifically, we've noticed three patterns in the field that are extremely important. Those are digital context, latent knowledge, and oversight. So digital context is just the sort of business fluff way of saying abstractions that are object-oriented data models that live between the customer's world and the solution world. So let me break this down a little bit. The first pain point we've discovered is that most solutions that tend to fail with the wrong what fail at the data bottleneck. So we're all here familiar of like data quality issues, data completion issues. Even in some of the discussions we've heard earlier, for example, in the context of fairness, is how do you ensure that your distribution is equitably reflected? But that's not what we mean here. We mean something actually much more practical and tangible, which is most enterprises and governments have multiple siloed data sources that don't engage with each other, have too many tables that they themselves don't understand, and have no way to digitally represent what it is that they actually do. And if I can't digitally represent your system, I have no chance at actually creating an effective component within the system. So what does this mean? There's sort of three schools of thought that we see in the field on the digital context piece. And sometimes people think they're competing, but they're also sometimes complementary. The first is you can solve this problem by building an object-oriented data model that acts as an abstraction layer between the various data sources and the system you're going to build. And you can build this data model with a human-centric lens, where the goal is to refactor and ETL all of my tables in a way where my objects and the links between the objects represent the ways humans think about the world. So that's sort of the first school of thought. The most famous example is my previous employer, Palantir. They have this thing they call the ontology, which is essentially a human-centric and a human lens-oriented way of looking at an object-oriented data model. The second school of thought is around process-first object-oriented data models. Sort of the best example there would be a company called Celonis and their OCDMs, where the idea there is to model your siloed data systems in a way that particularly emphasizes the processes over the actual entities or semantic entities involved. There, the goal is to unlock bottlenecks in systems and be able to actually maybe even replicate or automate these processes. And then the third school of thought, which is where we come in, and that's sort of where we're the biggest player, is building the data models in a, let's call it, NLP-first way. So you're building the model with the context of maximum ingestibility by LLMs or computer vision models for productive use. So it's sort of neither process heavy nor human heavy, and it sometimes has the advantage of being more efficient, but the disadvantage of being less human readable. So this is that first piece. The second failure mode we see in the field is that an incredible amount of work that occurs specifically in governments, but also happens in enterprises, relies on non-codified latent knowledge. There is so much stuff in people's heads that are convolved with the way they interact with the world that is not codified anywhere. And a lot of times, and you'll see this with these sort of narrow vertical solutions, there's no effort put in to digitize the sort of decision-making schemas that live in people's heads and the prioritization schemas that live in people's heads in a way that enables them to be digitally consumed. So the second piece here is about capturing that sort of latent and bespoke knowledge that is in people's heads in a way that's productive for your system. Now, this takes many different forms depending on the solution you're building. Sort of the most common and easiest form is what you'll often hear in the field being called discovery, where you actually have a human who goes and sits with the customer, embeds in their world, understands what they do, and works with them to either build out with maybe like point-and-click tooling, processes that are then put together into like some interesting schema for ingestion at inference time, or maybe even you build a system for them to use where you capture their interactions as logs and you use that. Or some of our work, for example, with the Mayo Clinic, you actually just undertake a data labeling exercise with the customer to extract that knowledge and set it up for ingestion. And the reason I say this high-level term ingestion is because this here could be done with like simple methods like simple K-shot learning, or it could be very extreme by having like an RL environment where you're constantly modifying the weights of the models that you're using and everything in between. And funnily enough, this component here ends up being the primary bottleneck that is associated with this touch grass problem I talked about earlier when it comes to evals. One of the biggest failure modes we see in the field is oftentimes people try to apply academic-style evals onto enterprise and government applications, where I have a semi-static data set that has some sort of verifiable outcome that I quantify, whether it be like a rubric or you know, a particular score that I can quantify, and then you just run evals on a system and try to quantify some sort of accuracy number. You say, hey, this like system is 70% accurate, is 80% accurate. Well, realistically, that actually ends up being very uncorrelated with what happens in the world. And I'll give you a concrete example. Some of our work in healthcare is about automating the process of like medical coding of doctors' notes. If you go in with an eval system that focuses on like model performance or automation performance, and you do it very academically, you end up with like a model that gets better on some sort of score that tells you how good is it at autonomously tagging these components. Then you go out in the field and you find out, wait a minute, I'm now trying to track the performance and speed by which people are flagging issues in these notes. And the difference between a 60% accuracy model and an 80% accuracy model is roughly 0. And the reason is because there's a real bottleneck there, which is the human aspect that is completely independent of the accuracy of the system, and then also the eval sets are not going to be very strongly correlated with the actual in-field work, because they sort of sometimes are over-sanitized or miss very important subtleties with the way the actual doctor is thinking about the problem that they don't actually put into their notes. The final piece is oversight. I don't mean this in the academic scalable oversight sense. I mean it in the much more practical, I have a stochastic system that I'm using to partially automate something, and now I need to either safeguard against incompetence or malice. And I know there's some malice directions that are going to be talked about later today and maybe have been mentioned earlier. But the idea there is that I need an observability stack, often dependent on how good my logs are, that will help me identify when an anomaly occurs and pull in a human to intervene mid-anomaly. For the sake of time, I'm going to sort of move over to the next component. But roughly speaking, the right what involves those things we talked about, and it sort of involves sort of marrying the thinking between how the users actually think about the world and the academic context associated with the models. Now, the biggest problem is the how. Roughly speaking, the issue here is that people keep treating these extremely stochastic systems like they are traditional software, and they try to deliver the solution in a way that is not friendly to that approach. Okay, what does that mean? I'll give you the answer up front, and then I'll explain it a little bit with an analogy from my previous career. The right how is the forward deployed engineering method, which is highly iterative in the field work to ensure that the thing you're building scope creeps in a positive direction that brings value to your customer. And I found that this sentence means nothing to most people, so I came up with this interesting, very concrete analogy from my past. So I used to work in spacecraft development, and these are two projects that I've worked on that are incredibly similar in scope, but extremely different in style of execution. So first is called Euclid, the second is called SuperBIT. They have roughly the same goal. The goal doesn't matter for the context of this conversation. But one of them uses what we call the old space method, or the systems engineering approach, where you have a very expensive launch. It's going to cost you a lot of money. And in order to safeguard against the cost of that launch, you build the system knowing everything a priori. You come into the build having determined what features, what submodules am I going to have, what specs do they need to have, and then you custom build every single component and assemble a system. It's incredibly effective and incredibly expensive. So you end up with a system here that costs about $1 billion and works really, really well. Now, the problem we were facing is, well, in this post-SpaceX era and post-stable suborbital balloon launch era, launches have gone really, really cheap. So the question is, can I do the exact same thing in a much cheaper way? So we said, hey, let's just try things that are not intended for space and see how they behave. And you'll see now why this analogy kind of works. By trying things that are not custom designed for this environment, what I did is I took my old hyper-predictive approach, where I knew exactly how each component is going to behave, and instead, I made sure that every single module now is completely random in behavior. At launch time, I don't know whether this module will work, fail, but in a predictable, understandable way that I can then modify for the next launch, or fail so miserably that I have to completely from scratch rebuild that entire component of the spacecraft. So we had to come up with a methodology to work with this new stochasticity that we've injected in our system, a stochasticity that's very similar to what happens when you inject a LLM, for example, as the core component of a use case in the field. And we came up with this approach. We call it closed-loop engineering. And the idea there is define your spec, build the simplest, fastest MVP you can, and just launch the damn thing. And then once it's launched, do very deep analytics to understand what's going on, what's failing, and how. Take that feedback, and then just simply refine your modules. And the categories that I mentioned earlier is you either rebuild the module completely, or you simply make intelligent modifications to the modules, or you get lucky and you don't actually need to make a change. And then you just keep running into this loop some large number of times until things work. And in the context of these two examples, it actually worked. SuperBIT ended up working really well for only $20 million, but it did require 6.5, depending on how you count, iterations of this loop. We had to launch it 6 times. Luckily, the launches are very cheap now. Now, the reason this analogy works is because this is kind of the whole mapping between systems engineering and closed-loop engineering is the same as the mapping between classical SDLC and forward-deployed engineering. Where forward-deployed engineering is the exact same thing as the closed-loop thing, where I have a problem, a quantifiable problem. There's a process in government or in an enterprise that's too slow, and I want to speed it up. Rather than designing a solution that solves the problem, I build the simplest possible thing that addresses a small percentage of the problem, and I just ship it. And instead of protecting against the scope creep, like I normally would have in traditional software development, I actually allow the scope to creep. So I launch it to the users, and I kind of let the user interaction determine what does and doesn't work. Now, this means I have to get really, really good at dynamic evaluations, as well as the soft human component of user testing. And then I take this feedback, I reiterate. With every reiteration, I make sure that I'm grounding against the original problem I'm trying to solve, and I keep running this loop until I go from, let's say it's an efficiency problem, I go from 10% efficiency increase to 20% to 30% to 40% to 40% to 40%. And once I've seen three 40% in a row, now I know I've either plateaued and I need to stop iterating or get more creative, or we're pretty much done. Now I have something that's useful. So the main failure mode we see with the wrong how is because people try to do this waterfall method or even classical agile to build these systems. You end up in this world where you have two options. Option one is build a system that does a single iteration of this loop. And that's how you end up with those systems that go into production but aren't very useful. Because in order to go through the loop once correctly, you have to design something that's relatively simplistic. That's why you see like this sort of an absurd amount of RAG chatbots flying around. Or your other, the other approach you could take is you can say, well, you know, I can just not do this loop altogether. I can just design the whole thing up front. But the likelihood of you being able to, in the lab, eval your solution to the point where you know exactly how it's going to work is roughly zero. And that's how you end up with those brilliantly thought out through solutions that never actually make it to prod. And I think I'm a little bit over, but I think with that, we can take it to Q&A. Thank you.
Stands.
Hi. First of all, thank you for the informative session. It was amazing. I have two questions. The first one, what is the characteristics or skills that makes you a good project manager or a huge project manager? And the second one, in this insanely speed field, how to keep up updates to the new technologies?
So these are both great questions. So let me answer the first one with a bit of a spicy answer. At scale, and in my department, we do product management, quote unquote, very differently. We still call them product managers, but we believe that in this new world, what a good product manager looks like is very different. They're much more technical. So we actually look for incredible technical skill. You're normally either ex-engineers or ex-researchers. But it's also business savvy, because in the modern era of product management, you're very customer-facing, and you're very goal-oriented with regards to the value you're trying to drive for the customer, because generally everything is bespoke. But the third and most important one is, I call it the double pull mitigation. So in the context of the forward deployed motion, you always have a go-to-market team that's pulling you to go faster and less grounded on good technology, and you have an engineering team that's always pulling you to go slower and more grounded on safer technology. So a really good forward deployed product manager or deployment strategist, whatever term, depending on the company you want to use, is really good at making the tough decision and the cost-benefit analysis between faster, less grounded decisions and slower, more grounded decisions. So that's, I think, the first question. Can you remind me what the second question was?
How to keep up updates in this insanely speed field?
Okay, here's sort of my hot take on this. Despite being super into both the research side and the applied side, I always feel out of date. So I've accepted that this weird feeling of like not always being up to date is just part of this new world. But I can tell you what I personally do. This is not an endorsement of any particular model, but I made a Claude skill that I use and I spend about 6 hours a week, where the Claude skill goes and fetches some news for me, and then I iterate with Claude on the things I think are interesting and decide what things I don't want to go deep on. And that's sort of the best solution I've had so far, but I still do feel behind almost all the time.
Thank you so much.
Of course, thank you.
Thank you so much for your talk. It was really nice to get more of a product kind of oriented talk compared to more like academic talks, and I think it's very interesting to have a business oriented perspective on this. So yeah, I come from an engineering background as well, and yeah, you kind of in lectures you always kind of get this agile versus like water flow kind of perspective. And I saw that obviously here we're kind of saying that it's because people are taking more of a waterfall like perspective that these kind of prototypes are failing. But I feel like, obviously, at the moment with AI, like, what's like the main difference between traditional software engineering, where we're saying agile is helpful and everyone should go for agile, that's kind of like not successful with AI. I think it maybe goes a bit further than agile in some ways, right? Maybe it's also because coding has become so democratized and vibe coding is just so easy that a lot of people just try to develop and deploy solutions in a very kind of, yeah, just, you know, let's throw it out there and it works. But yeah, don't try to kind of do it in a critical and yeah, useful way. So
it's a great question. So let me start by saying I actually would put agile and waterfall both in the systems engineering category, because agile is still a little bit too traditional in the sense that, yes, it's iterative, but it's often iterative at the feature level as opposed to at the problem level, because it's normally thought of from the perspective of building a particular solution in a particular environment. I call it like proactive product management. So if you're at a company, it's building a particular piece of software, and that software is your product. So to answer your question is, I think the way this forward deployed engineering motion differs from agile is a few ways. First is it has an almost consultancy feel to it, as much as I hate to admit that, because the idea there is you're assuming that as a function of time, the cost of writing net new code decays very quickly. I'm not going to go as far as to say it goes to roughly zero, but as you said, with like vibe coding tools and so on, decays very, very quickly. So my ability to iterate and take much larger swings back and forth in my iterative process gets easier and easier as a function of time. So the core difference between like an agile approach and a forward deployed engineering approach is that mechanistic layer by which I get very repeated signal from the customer and from the user. And here the reason I differentiate those two things is because oftentimes when you're building bespoke solutions, your customer is not your user. Your customer is some budget holding individual who probably has never met the user and also doesn't really know the workflow that you're trying to fix. So one of the interesting things we've noted, for instance, is that having both your technical leads, often even our researchers and our product folks in the customer's office a couple of days a week, where they are themselves upskilling as power users. Having them upskill in the sort of latent knowledge direction associated with the field, right? So if you're working in insurance, I expect my team to go and become almost as good as any other underwriter in the field. When I was in the field back in the day, I had a situation where I was working with an unnamed tire manufacturer, and I couldn't do my job if it wasn't for the fact that I went and spent 3 weeks acting as a point of sale individual, literally dealing with the tire return system in order to sort of understand where the actual pain points are. So that's on the like information gathering layer. On the reaction layer, it's a bit complicated because the sanitized answer is, well, you just ignore things like good UI and you ignore things like user satisfaction. You just go against the workflow, but then you'll churn the customer. So it's the balance between what is the fastest I can iterate and swing back and forth without causing such a complex change management bottleneck that I completely lose my customer and my customer's ability to use the technology. Because it doesn't matter how useful the thing is if no one uses it.